In the constellation Phoenix, 100 million light-years away, a black hole is eating so fast it should blow itself apart. Astronomers call it HLX-1, an ultra-luminous X-ray source. The problem lies in a fundamental limit of astrophysics, the Eddington limit. As matter falls toward a black hole, it compresses and radiates. At a certain luminosity, the outward pressure of that radiation overwhelms gravity, pushing the infalling gas away. This sets a maximum feeding rate for a typical stellar mass black hole. That limit corresponds to a luminosity about 100 million times our Sun. HLX-1 exceeds its own Eddington limit by a factor of at least 100. The radiation should be shutting down the feast, yet the black hole persists. And it is not alone. Over the past 2 decades, X-ray observatories like Chandra and XMM Newton have catalogued dozens of objects that appear to surpass the Eddington limit by factors of 10, 100, even 1,000. If these observations are correct, something fundamental is wrong with our understanding of how black holes feed. The stakes extend beyond a single puzzle. This apparent loophole may explain how the universe's most massive black holes grew so quickly in the early cosmos. How can a black hole swallow matter at such a furious rate without choking on its own radiation? The answer begins with the physics that defines the limit itself. To understand why that limit exists, we first need to see how a black hole actually feeds. Matter rarely falls straight into a black hole. It comes from a companion star or a cloud of gas, and because of angular momentum, it doesn't plunge directly in. Instead, it spirals into a flat, rotating disk, an accretion disk. Imagine water swirling down a drain, but in this case the drain is a gravitational well so deep that nothing, not even light, can escape once it crosses a certain point. Inside the disk, friction and viscosity create a kind of cosmic drag. Gas rubs against gas, and as material slowly moves inward, gravitational potential energy is converted into heat. The disk gets hot, tens of millions of degrees, and begins to glow, mostly in X-rays. How close can the gas get before it crosses the event horizon? There is an inner boundary called the innermost stable circular orbit, or ISCO. Inside that radius, material can no longer maintain a stable orbit and falls almost freely into the black hole. This whole process is remarkably efficient. Roughly 10% of the infalling matter's rest mass energy gets converted into radiation as it spirals inward. That is why accreting black holes are among the brightest objects in the universe. But here is the crucial point: the radiation itself carries momentum. The same X-rays that let us detect these black holes also push back against the gas trying to fall in. That creates the Eddington limit, a natural ceiling on how fast a black hole can feed under spherical, steady conditions. But as we are about to see, there are ways around that ceiling, ways that involve the very structure of the accretion disk itself. Here is the key: every photon that escapes the accretion disk carries momentum. When a high-energy X-ray smacks into an electron, it gives that electron a tiny kick outward. In a fully ionized gas, electrons and protons are bound together by electric forces, so that kick transfers to the whole plasma. That outward push is radiation pressure, and it grows with the luminosity of the disk. Gravity, on the other hand, pulls the plasma inward. For a given black hole mass, there is a specific luminosity at which these two forces exactly balance. Inward gravity and outward radiation pressure cancel each other. At that luminosity, the infalling gas would come to a halt. That balance point is the Eddington limit. Arthur Eddington first worked this out not for black holes but for stars. He wanted to know how bright a star could be before its own radiation blew it apart. The same physics applies to an accreting black hole. The formula itself is remarkably simple. The Eddington luminosity is proportional to the mass of the black hole. A black hole 10 times the mass of the Sun has an Eddington luminosity of about 10 million trillion watts. A billion solar mass supermassive black hole has an Eddington luminosity that is 100 million times larger. That direct proportionality makes the limit an incredibly useful tool. When astronomers detect a luminous accreting black hole, they can assume it is shining at or below its Eddington limit and then estimate its mass from the luminosity alone. But the classical derivation makes several assumptions. It assumes the accretion is spherical, that the gas is steady, that it is pure ionized hydrogen, and that no magnetic fields or beaming are twisting the geometry. Under those ideal conditions, the limit is a genuine ceiling. Go even 1% above it and the radiation pressure should overcome gravity, pushing the infalling gas away and choking off the fuel supply. For decades, this was the rule. Astronomers expected that no steadily accreting black hole could ever be observed shining above its Eddington luminosity. It was a bedrock assumption until the telescopes started revealing sources that simply refused to obey. X-ray telescopes like Chandra and XMM Newton revealed point-like sources in nearby galaxies far brighter than neutron stars could produce. Their luminosities often exceeded the Eddington limit for a 10 solar mass black hole by hundreds of times. The most famous outlier is HLX-1 at the edge of galaxy ISO 24349, 290 million light-years away. Its X-ray luminosity peaks at 1 times 10 to the 42 ergs per second. For a 10 solar mass black hole, the Eddington limit is about 3 times 10 to the 39 ergs per second, meaning HLX-1 would shine at over 800 times its ceiling. Even at 50 solar masses, it would still be 20 times above Eddington. Only if the black hole exceeds about 500 solar masses could the luminosity fit within the limit. But no stellar mass black hole from a supernova reaches that mass, so either HLX-1 is an intermediate mass black hole, a class that remains elusive, or it is a smaller black hole accreting far above the limit. And the puzzle extends to supermassive black holes. The quasar J2157 3602, at 34 billion solar masses, has a bolometric luminosity near 7 times 10 to the 47 ergs per second, roughly 300 times its Eddington limit. Its distance and mass are well constrained, so the numbers appear robust. A growing sample of such objects presents the same stark discrepancy. The observations demand an answer, but first we need to consider if the measurements themselves could be misleading. Could the numbers be wrong? Luminosity depends on flux and distance squared. Double the distance and the luminosity quadruples. Underestimate the distance and you overestimate the brightness. For some ultra-luminous X-ray sources, distance is uncertain. If HLX-1 were closer, its luminosity would drop, but its host galaxy ESO 24349 has a well-measured redshift, so the distance is secure within a few percent. And for quasars like J2157 3602, the redshift gives a cosmological distance that is essentially unambiguous. Distance alone cannot erase the anomaly. For some sources, revised distances have lowered the ratio, but for these objects the distances are secure. The other uncertainty is mass. The Eddington limit scales with the black hole's mass. If we underestimate the mass, the ratio falls. A 10 solar mass black hole has a strict ceiling, but a billion solar mass one has a much higher one. So could these sources be more massive than we think? For stellar mass black holes in our galaxy, dynamical mass measurements from companion orbits are possible. But for extragalactic ULXs, astronomers rely on X-ray variability or disk spectral shape. For HLX-1, timing suggests a mass around 10,000 solar masses, yet its peak luminosity still exceeds the Eddington limit by a factor of 10. Reducing the ratio below 1 would require a mass far beyond what the timing data permits. Mass estimates for ULXs are indirect, but even with conservative assumptions, the ratio remains high. For quasars, mass is estimated from emission line widths and broad line region size. J2157 3602's mass of 34 billion suns is consistent across methods. Raising it enough to bring the Eddington ratio below 1 would require a mass approaching 1 trillion suns, which would contradict the host galaxy properties and the spectral line widths. So if the luminosity is real and the mass is not wildly wrong, how can so much radiation escape without sabotaging the accretion flow? And when you look beyond the most famous examples, you find that this feeding behavior is not a freak occurrence. It is practically everywhere you point a sensitive X-ray telescope. A whole zoo of objects across the mass scale shows the same apparent violation. Start with stellar mass black holes in our own galaxy. The microquasar SS433, about 18,000 light-years away, powers jets moving at 1/4 of the speed of light. To launch those jets, the inner accretion disk has to be dumping matter at rates well above its Eddington limit. Then there are the ultra-luminous X-ray sources found in nearby galaxies. NGC 1313 X2, for example, shines at around 10 to the 40th ergs per second. For a typical 10 solar mass black hole, the Eddington limit is about 10 to the 39th. That is 10 times the ceiling, and those are just the close ones. At cosmological distances, quasars like J2157 3602 blaze at Eddington ratios approaching 100. So we have stellar mass objects, intermediate mass candidates, and billion solar mass behemoths all exceeding the same fundamental limit. The phenomenon spans the local universe to the cosmic dawn. That consistency makes it impossible to write off each case as a unique accident. Something systematic is allowing black holes to bypass the old ceiling. What mechanism could be powerful enough to let a black hole consume at 10 or 100 times the theoretical maximum without tearing itself apart? Perhaps the radiation is not spreading evenly in all directions. If the black hole's accretion disk or inner jet happens to point almost directly at us, we are looking down a narrow funnel where light is concentrated like a flashlight beam. This is a well-known effect in astronomy. A blazar can appear thousands of times brighter than its true power because its relativistic jet is aimed our way. The apparent luminosity becomes an illusion of perspective, allowing the black hole to feed at a sub-Eddington rate while appearing to break the limit. That idea is attractive because it preserves the Eddington limit as an absolute barrier, but many ultra-luminous X-ray sources do not look like beamed emitters. Their X-ray spectra are soft and thermal, dominated by emission from a hot accretion disk rather than the non-thermal glow of a relativistic jet. They lack the extreme variability and superluminal motions that would signal a pointed jet. If beaming were the universal explanation, we would expect more jet signatures across the population. Instead, the majority show a broad thermal bump consistent with a thick, geometrically inflated disk. So beaming can account for some cases, perhaps the most extreme ones, but it cannot be the single solution. For every apparently beamed ULX, there are many more that appear to be standard accretion disks shining far above the limit. If the light is not being artificially compressed in our direction, the problem moves inward. The radiation really is that intense, and the black hole really is feeding that fast. That forces us to re-examine the physics inside the accretion flow itself, where the old rules about radiation pressure controlling accretion may not apply as we assumed. So we need to look inside the accretion flow itself, where the old rules about radiation pressure controlling accretion may not apply as we assumed. The classic picture is a smooth, uniform disk where photons are generated evenly and push outward with a force that scales with the local intensity. But that assumption of uniformity is exactly what breaks down under extreme conditions. Think of a pot of water on a high flame. If the heat is intense enough, the water doesn't just get hot, it boils, forming bubbles of vapor that rise and burst. Those bubbles are regions of much lower density than the surrounding liquid. Now imagine the same process inside a radiation pressure-dominated accretion disk. The disk is so fiercely heated that the radiation itself drives instabilities. Slight fluctuations in density create pockets of lower opacity under dense bubbles, through which photons can stream outward much faster than through the denser material. This is the photon bubble instability. The result is a disk that is not a solid wall of gas but a porous, frothy structure. Photons escape through these low-density channels, so the net radiation force on the bulk of the matter is reduced. The effective opacity of the disk drops, and the critical luminosity at which radiation pressure would halt the inflow rises. Detailed three-dimensional magnetohydrodynamic simulations have confirmed that photon bubbles can sustain accretion rates several times above the classical Eddington limit, in some cases up to an order of magnitude higher. That is a concrete piece of physical machinery. Nature builds a sieve into the disk itself. The radiation is no longer trapped in a uniform blanket pushing against the infalling gas. It finds a path out through a network of low-density tunnels. The black hole can keep feeding because the radiation doesn't have to fight its way through every gram of matter. Photon bubbles are not speculation. They are now a standard ingredient in models of super-Eddington accretion, observed in simulations and consistent with the soft thermal spectra of many ultra-luminous sources. They show that the Eddington limit is not a fixed wall but a barrier that can be pushed higher when the disk becomes structured. And yet, even this trick may not be enough for the most extreme objects. The story is far from over. Magnetism is another invisible force woven into the accretion disk. Accretion disks are ionized plasma, and the infalling matter carries magnetic fields. Those fields get stretched and twisted by rotation, triggering the magnetorotational instability, or MRI. Magnetic field lines act like springs connecting neighboring layers of the disk. The inner part spins faster, so it winds the field line like twisting a rubber band. That tension pumps turbulence into the disk, and that turbulence transports angular momentum outward, which allows material to keep falling inward. Without magnetic fields, accretion would grind to a halt. The MRI is the engine that powers the whole feeding process, but near the black hole, magnetic fields do more. Magnetic pressure can grow to rival radiation pressure. The field lines become stiff, anchoring the disk and reaching down to the event horizon. Through the Blandford-Zeenagic process, the black hole's spin energy can be tapped, launching powerful jets and extracting rotational energy. This reshapes the disk completely. It is no longer a simple thin sheet of gas. It becomes a magnetic fortress where the field lines support the weight of infalling matter and channel radiation in specific directions. So magnetism is not an afterthought. It is a central player capable of reshaping the entire accretion flow. When these fields become strong enough, they open the door to a different mode of accretion. A disk that can trap its own radiation. That mode is the slim disk model. In the standard thin disk, the disk is geometrically thin, like a flat pancake. Photons produced by friction and heat have a relatively short path to escape, so they stream away efficiently. Radiation pressure builds up, and eventually it balances gravity, setting the Eddington limit. But when the accretion rate climbs far beyond that limit, the disk cannot stay thin. The inflow is so rapid that the disk puffs up, becoming geometrically thick with a height comparable to its radius. And it becomes optically thick, meaning photons cannot simply escape. Here is the crucial insight. In a slim disk, photons are generated faster than they can diffuse outward. The radiation field becomes trapped in the inflowing gas. Instead of pushing outward and halting accretion, those photons are carried along with the matter, advected toward the event horizon, and swallowed by the black hole before they ever exert their full pressure. This changes everything. the radiation pressure never builds to the level that would blow the disk apart. The luminosity climbs, but it saturates near the Eddington value, while the extra energy and mass flow disappear into the black hole, adding to its mass. So the object can have an accretion rate tens or even hundreds of times the Eddington rate, yet appear only a few times brighter than the Eddington luminosity. The black hole gets fat, but the light does not reflect that gluttony. There is observational support for this picture. Many ultra-luminous X-ray sources show thermal X-ray spectra that match what slim disk should produce. The spectral shape and the way the disk temperature scales with luminosity follow the slim disk predictions, not the thin disk model. This gives astronomers confidence that something like photon trapping is actually happening. But even slim disks have their limits. They naturally cap the luminosity at roughly an order of magnitude above Eddington, yet some objects exceed that comfortably. And that is where the story takes a more radical turn, because when the accretion rate becomes truly extreme, the disk does not just get thick. It begins to fight back with magnetism, creating a mechanism that can push the brightness even higher. As matter falls toward the black hole, it drags the accretion disk's magnetic field lines inward. If the accretion rate is high enough, magnetic flux accumulates near the black hole until its pressure balances the ram pressure of the inflow. The disk becomes magnetically arrested, or MAD for short. Imagine a traffic jam of magnetic field lines piling up at the gate. The jam does not just slow the flow. It can stop it. The infalling gas gets pushed back by the magnetic wall, and accretion becomes episodic. Magnetic pressure builds, blocks the inflow, then reconnection or a sudden instability releases a blob of gas. The result is a burst of intense accretion and a flare of extreme luminosity, often far above what a steady flow could produce. The black hole feeds in short, intense episodes rather than a continuous feast. Observations support this picture. Some ultra-luminous X-ray sources vary by factors of 10 in hours or days, exactly the pattern of a magnetic dam breaking and rebuilding. Many also launch powerful jets and fast outflows, natural products of a magnetically dominated environment. During a magnetic eruption, luminosity can spike to tens or even hundreds of times the Eddington value, while the time-averaged accretion remains within what the disk can sustain. Simulations show that this MAD state can form when the magnetic flux is strong enough, and it naturally explains the extreme variability and outflows seen in the most luminous ultra-luminous X-ray sources. But a magnetically arrested state requires a delicate balance, enough magnetic flux to stop the flow, but not so much that accretion halts entirely. If the inflow drags in too much new flux, the disk may choke permanently. If it drags too little, the magnetic jam never forms. The conditions for this balance are not fully understood, and it remains unclear how long such a configuration can last. The disk has another pressure relief valve. Instead of stalling accretion, it can launch a powerful wind that carries away mass, momentum, and radiation pressure. The outgoing gas reduces the density of infalling material and sweeps out the photons that would push against the disk. This creates a self-regulating system. The wind vents excess pressure, allowing fresh gas to keep falling in, sometimes at super Eddington rates. We see these outflows directly. The microquasar SS433, a stellar mass black hole in our galaxy, drives jets and slower winds that produce P Cygni spectral lines, revealing gas moving toward us at thousands of kilometers per second. Ultra-luminous X-ray sources often show blue-shifted absorption lines, indicating outflowing material at a fraction of the speed of light. These outflows are not secondary. They let the disk survive. Observations and simulations converge. For a black hole accreting well above the classical limit, the disk breathes out a wind that removes the worst of the radiation load. By shedding mass and radiation, the remaining disk sustains a higher Eddington ratio for the same luminosity. the black hole keeps eating but pays a tax. A significant fraction of infalling matter is thrown back into space. That trade-off is acceptable because the net accretion rate remains enormous. Some explanations for ultra-luminous X-ray sources avoid super-Eddington accretion altogether. If the black hole is significantly more massive than estimated, its Eddington luminosity rises and the observed brightness drops below the limit. An intermediate mass black hole of tens of thousands of solar masses would make many ULXs ordinary. But independent evidence for such black holes is weak, and the few candidates remain disputed. More speculative proposals include primordial black holes from the early universe, or exotic compact objects like boson stars and gravastars with altered radiation properties. Dark matter accretion is another possibility, though dark matter does not produce X-rays directly and would require exotic annihilation models that have not matched observations. None of these alternatives are ruled out, but they carry a heavier burden of proof. The physical mechanisms already discussed, slim disks, photon bubbles, magnetic arrest, winds, are grounded in tested physics and reproduced in simulations matching real data. Yet the standard picture is not complete. Every model makes assumptions about disk geometry, magnetic field strength, and radiative transfer efficiency. We still cannot peer into the innermost accretion regions directly. The most extreme super-Eddington sources may combine all these tricks at once, and we are only beginning to untangle their relative contributions. Photon bubbles, slim disks, magnetic fields, magnetically arrested disks, and winds each work alone, but nature rarely relies on a single trick. The real story is how these mechanisms layer together, tuned by each black hole's specific conditions. For mild super-Eddington rates, the disk becomes geometrically thick and radiatively inefficient, trapping photons and advecting them inward. Photon bubbles create low-density channels that let radiation leak faster, reducing effective opacity. Together they push the effective Eddington limit upward by a factor of a few, enough to explain many ultra-luminous X-ray sources. For extreme rates, tens or hundreds of times the classical limit, magnetic fields dominate. A magnetically arrested disk builds up strong magnetic flux near the black hole, periodically halting inflow. When the field reconnects, it releases a burst of energy, momentarily exceeding the Eddington limit by orders of magnitude. Outflows and jets carry away momentum, allowing the disk to survive. This is not a chaotic mix of exceptions but a coherent physical framework. State-of-the-art three-dimensional general relativistic magneto-hydrodynamic simulations routinely produce super-Eddington luminosities by incorporating these effects simultaneously, matching observed X-ray spectra, variability patterns, and outflow velocities. The classical Eddington limit is recovered only under idealized assumptions of spherical symmetry, no magnetic fields, and steady-state accretion, conditions nature almost never meets. The universe has multiple ways to cheat, and it uses them. This realization shifts the question from whether super-Eddington accretion is possible to how common it is, and what it means for black hole growth across cosmic time. So where does this leave the Eddington limit itself? The classical version, taught for nearly a century, was derived under assumptions that almost never hold in practice. Spherical symmetry, no magnetic fields, steady-state flow. Nature is messier. The real limit is an effective one that depends on geometry, magnetic support, radiation trapping, and outflows. For a slim disk with photon bubbles, the effective limit rises by a factor of a few. For a magnetically arrested disk, it can jump by orders of magnitude during flares. In other words, the old single number becomes a variable ceiling, one shaped by the specific conditions around each black hole. This is not a minor tweak. It means the classical Eddington limit is not a hard ceiling but a useful baseline, a reminder of what happens in the simplest possible case. The real physics allows much higher accretion rates and therefore much shorter growth timescales. That changes everything about how quickly supermassive black holes can form. Instead of requiring billions of years to reach 1 billion solar masses, early universe quasars could grow in a few 100 million years if they spend time in a super Eddington mode. Galaxy formation simulations now routinely adopt adjustable Eddington factors because a single fixed limit fails to reproduce observed black hole populations. The central paradox that opened this investigation, how a black hole can eat so fast it should blow itself apart, is resolved. The answer is that it does not violate a fundamental law. It violates a simplified textbook formula. The real universe uses a richer set of rules, and those rules allow the kind of rapid feeding seen in ultra-luminous X-ray sources and hyperluminous quasars. With this revised understanding, a cascade of consequences follows for the most massive objects in the universe. The mass of a supermassive black hole correlates tightly with the velocity dispersion of stars in its host galaxy's bulge. This M-sigma relation points to deep co-evolution. As a galaxy grows, its central black hole grows with it, and the black hole shapes the galaxy through feedback. Super Eddington accretion resolves how that relationship can exist. During brief growth spurts, a black hole can feed many times above the classical limit, reaching its final mass early in its galaxy's life, well before the galaxy finishes assembling its stars. Then the same physics that enabled rapid growth drives powerful outflows that expel gas, shut down star formation, and regulate evolution. The observed M-sigma relation becomes a natural signature, not a puzzle. Consider NGC 4889, a giant elliptical whose central black hole weighs roughly 21 billion solar masses. Under Eddington limited growth, accumulating that mass would take far longer than the age of the universe, yet the galaxy is already fully formed. Super Eddington spurts make such rapid growth possible. The tight correlation between black hole mass and galaxy properties no longer demands exotic explanations. It is a record of fast, efficient growth tied directly to the feedback that shapes galaxies. This rapid growth is especially critical for explaining the behemoths we see in the early universe. The rapid growth required by the M-sigma relation finds its most extreme test in the early universe. Quasars at redshift 6 or higher, when the universe was less than 1 billion years old, host black holes of 10 billion solar masses or more. SDSS J0100 plus 2802, for example, harbors a black hole of roughly 12 billion solar masses. Under the classical Eddington limit, such growth seemed impossible. The E-folding time at the Eddington rate with 10% efficiency is about 40 million years. To go from 100 solar mass seed to 1 billion requires 20 doublings or 800 million years, almost the entire age of the universe at that time. From a stellar seed, standard growth simply cannot reach billions within the available time. Super Eddington accretion changes that calculation. At 10 times the classical limit, the E-folding time drops to 4 million years, and the same growth takes just 80 million years, leaving hundreds of millions of years to spare. And super Eddington rates are physically plausible, especially in the gas-rich environments of the first galaxies. Surveys like the Sloan Digital Sky Survey and Subaru Hyper Subprime CAM have uncovered dozens of high redshift quasars whose masses demand either super Eddington growth or impossibly massive seeds from direct collapse. The evidence strongly leans toward super Eddington accretion as the standard path. This is the concrete discovery. The same physics that explains an ultra-luminous X-ray source in a nearby galaxy also explains the rapid emergence of the largest black holes in cosmic history. The local mystery and the cosmological crisis are two sides of the same coin. The same physics might also be creating intermediate mass black holes, the missing link between stellar and supermassive objects. These black holes range between 100 and 100,000 solar masses, too large to form from a single star but too small to anchor a galaxy. For years, astronomers have suspected that some ultra-luminous X-ray sources are exactly these IMB, accreting at ordinary rates. An IMB of 10,000 solar masses radiating at 1/10 its Eddington limit would still appear incredibly bright. So a ULX could be normal accretion onto an exotic object, but the other possibility is that these ULXs are stellar mass black holes undergoing the super Eddington feeding frenzy we have explored with the high luminosity reel. Which scenario is correct matters because it tells us whether super Eddington accretion can build not just the biggest black holes, but also the middleweights that bridge the population. We can settle it by measuring the black hole's mass directly through orbital dynamics or gravitational waves. A stellar mass object radiating far above its Eddington limit points to the mechanisms we have covered. An intermediate mass object radiating below its limit would confirm that IMB are common. The future space-based gravitational wave observatory LISA will catch mergers of IMB if they exist, revealing whether these feeding frenzies create a whole new class of cosmic objects. For now, the open question is whether the super Eddington firehose is also an IMB factory, and we may not have to wait long to find out. A new generation of observatories is probing super Eddington sources with precision impossible just a few years ago. The Imaging X-ray Polarimetry Explorer (IXP) measures the polarization pattern of X-rays, revealing whether emission comes from a flat disk, a jet, or a wind. Early IXP observations of the ultraluminous X-ray source NGC 1313X2 show polarization consistent with a thick, modified disk rather than a narrow jet, favoring the slim disk or photon bubble models over simple beaming. The X-ray Imaging and Spectroscopy mission, XRISM, provides high-resolution X-ray spectra that detect blue-shifted absorption lines from outflows, measuring their velocity, density, and chemical composition. This tests whether winds carry away excess momentum as super Eddington models predict. The James Webb Space Telescope observes the host galaxies of nearby ULXs and distant quasars, using infrared sensitivity to pierce dust and measure black hole mass through stellar dynamics, or reveal the star formation history of the surrounding environment. That puts the Eddington ratio into context. Is the black hole growing in a gas-rich region that can sustain such extreme feeding? Together, these observatories are converging on the same question from different angles, distinguishing between a disk that genuinely glows far above the classical limit and one that only appears to due to beaming or a hidden intermediate mass black hole. The data we already have contains two clear signatures of super Eddington accretion. First is rapid X-ray flickering. When matter piles onto a black hole at extreme rates, the inner disk becomes thick and turbulent, producing small fluctuations in X-ray light. Sometimes those fluctuations organize into a quasi-periodic oscillation. The ultraluminous X-ray source M82X1 shows a clean repeating oscillation at a few tenths of a hertz. That frequency implies the emitting region is compact, only a few times larger than the black hole's event horizon, consistent with a thick, radiation-trapped slim disk that advects energy inward. No beaming or intermediate mass black hole model reproduces that stable oscillation period as neatly. The second signature is ultrafast outflows. These are winds of highly ionized gas streaming away at 0.1 to 0.3 times the speed of light. Astronomers detect them through blue-shifted absorption lines, typically from iron, in X-ray spectra. The Quasar PDS 456 is a textbook case with an absorption trough indicating gas moving outward at roughly a third of light speed. Only a powerful radiation wind or magnetically driven eruption can accelerate gas that fast, both natural consequences of an accretion flow far exceeding the classical Eddington limit. A sub-Eddington disk simply cannot produce such winds. Together, these two signatures, rapid variability pointing to a compact thick disk and relativistic outflows demanding extreme driving forces, form a coherent picture of super Eddington accretion. Yet even the smoking guns leave unresolved anomalies. The soft X-ray excess in many ULXs, an unexpected low-energy bump, is not naturally produced by slim disk models. Some explanations invoke a warm corona, but why it appears in only some sources remains unclear. The soft component demands an extra ingredient beyond the slim disk, but the exact mechanism remains unidentified. Non-thermal power law tales in a few ULXs point to jet activity or magnetic reconnection, raising the question of how much luminosity comes from accretion versus magnetic processes. The answer likely varies from source to source, making a one-size-fits-all model impossible. The presence of a jet component complicates the interpretation of the overall spectrum. The deepest tension is sustainability. At 100 times Eddington, a stellar mass black hole would exhaust its surrounding gas in a few thousand years. Yet ULXs shine for decades and some quasars for much longer. Either an efficient resupply mechanism is at work or the episodes are shorter than they appear. The longevity problem is particularly acute for supermassive black holes in quasars across cosmic time. Models have not proven that such extreme feeding can last millions of years. So while the broad outline is clear, nature does find ways around the classical Eddington limit. The details remain messy. The soft excess, the power law tales, the longevity question are loose threads that keep astrophysicists honest, and the black holes that eat too fast are far from finished teaching us. These are not failures of the model but signposts toward a deeper understanding. These outliers forced astrophysicists to see the Eddington limit not as an unbreakable wall but as a baseline derived from perfect symmetry. Nature breaks those assumptions through magnetic fields, radiation trapping, and geometry, allowing black holes to grow beyond the classical ceiling. This pattern is familiar from other physical limits like the Chandrasekhar mass or the sound barrier, each overcome when the right conditions are engineered. And it is this frontier thinking that leads directly to the biggest black holes in the universe and the gravitational waves they produce. When LIGO and Virgo detected GW 190,521, its progenitor masses of 66 and 85 solar masses posed a puzzle. The 85 solar mass object lies in the pair instability mass gap, where a collapsing star should blow apart rather than leave a black hole, a likely solution. The black hole started smaller and then grew by accreting at super Eddington rates. In a dense environment like the disk around a supermassive black hole in an active galaxy, a stellar mass black hole can rapidly gain mass. That growth spurt can jump the mass gap. This connection makes extreme accretion a frontline tool for interpreting gravitational wave data. If super Eddington episodes are common in dense clusters or AGN disks, we should expect black holes above the ordinary stellar upper limit and more mergers between disparate masses. Some of those mergers may produce intermediate mass black holes, building a bridge between stellar and supermassive regimes. LIGO and Virgo are already testing that prediction. So the black holes that break the Eddington limit are not just oddities in X-ray catalogs. They may be the invisible architects of some of the heaviest colliding black holes we have detected. The same outflows and jets that enable super Eddington feeding carry energy, momentum, and heavy elements into the surrounding space. When a black hole feeds at a super Eddington rate, its radiation pressure drives powerful winds, and its magnetic fields launch relativistic jets. These outflows plow into the host galaxy's gas, heating it and pushing it outward. Star formation can be abruptly shut off. The cold, dense gas needed to make new stars gets blown away or stirred into a hot, diffuse state. Astronomers have observed exactly this feedback in distant galaxies that host hyper-luminous quasars. Their X-ray spectra show blue-shifted absorption lines, proof that metal-enriched gas streams outward at thousands of kilometers per second. When we look at the most massive galaxies in the universe today, many appear red and quiescent, their star formation long finished. Simulations now suggest that a super-Eddington phase, even one lasting only a few million years, can clear out the remaining gas and leave a galaxy inactive for billions of years. The metals carried by those winds also escape the galaxy entirely and mix into the circumgalactic medium, enriching the reservoir from which future generations of stars and planets will form. The same black hole that once seemed to break the laws of physics is actually a major force in building the cosmic chemical abundance pattern and sculpting the largest structures we see. Its influence reshaped the universe long before most stars even existed. Push that scenario to its theoretical extreme. Imagine a young black hole, perhaps a few tens of solar masses, sitting inside a massive, collapsing gas cloud weighing thousands of times the Sun's mass. The black hole begins feeding not at 10 times the Eddington limit or even 100, but at 1,000 times the classical cap. At those rates, the energy released is so immense that it inflates a giant radiation bubble around the black hole, puffing up the surrounding gas into a structure called a quasi-star. The black hole sits at the core, swallowing matter faster than any steady accretion model predicted, while the outer envelope expands to a size larger than the entire solar system. From the outside, this object would outshine a galaxy, a single point of light blazing at a luminosity that old Eddington logic said was impossible. Such objects cannot last long. The envelope either gets blasted away by its own intense radiation, or the black hole eats through it in a few 100,000 years. The window is extremely brief, and the universe may have produced many of these hyper-Eddington monsters in its earliest epochs, seeding the supermassive black holes we see today. Astronomers have not yet confirmed a quasi-star, but some extremely luminous transients glimpsed at high redshift have properties that tantalizingly match predictions. The physics does not forbid them, it just requires a very special set of circumstances. So the question becomes not whether such extreme feeding can happen, but how we would recognize it if it did. Are there signals hidden in our data right now from these extreme events? And could the same hyper-Eddington mechanism be at work whenever a black hole suddenly receives a fresh gas supply? But this isn't just a piece of early universe lore. The same kind of sudden gas supply happens in our own cosmic neighborhood, and we've watched it unfold. When an unlucky star strays too close to a supermassive black hole, the black hole's tidal forces tear the star apart. The debris rains down in a rapid burst, forming a temporary accretion disk that initially feeds at rates hundreds or even thousands of times the Eddington limit. These are called tidal disruption events, or TD, and they give us a front-row laboratory for seeing super-Eddington physics in action. In the first weeks after a TD, the emitted light often blazes well above the classical Eddington luminosity. Take a Saturn 15 LH, a TD whose peak brightness exceeded the black hole's Eddington limit by more than 100-fold. For a short while, the black hole is as gluttonous as any early universe monster, but the feast is temporary. As the debris is either swallowed or blown away, the accretion rate drops and the luminosity decays below the Eddington threshold. That fast, bright phase matches exactly what slim disk models predict for super-Eddington accretion. Radiation gets trapped, outflows carry away excess energy, and the disk remains stable. Better still, TDs produce signatures we can study in detail. Some, like Swift J1644+57, show relativistic jets and ultrafast outflows, just as the magnetically arrested disk model predicts. Others reveal broad emission lines from winds moving at tens of thousands of kilometers per second, direct evidence of the radiation-driven relief valves we discussed. Every time we observe a new TD, we're watching the same physics that allowed black holes in the early universe to gorge themselves and grow into behemoths. The difference is that now, with modern telescopes, we can see it happening in real time, confirming that the mechanisms we've pieced together are not just theoretical, they are real, observable, and at work wherever a black hole suddenly gets a fresh meal. We watch these tidal disruption events unfold in real time, and each one confirms a deeper truth. The mechanisms we explored, photon trapping, magnetic arrest, outflows, instabilities, are not exceptions. They are nature's standard toolkit for building black holes far faster than our old equations ever allowed. The Eddington limit, long taught as an inviolable ceiling, turns out to be more of a guideline, one that the universe breaks with clever engineering. It reminds us that the most fundamental laws are often just the beginning of a deeper story. That story reshapes everything: how supermassive black holes grew in the first billion years, how galaxies co-evolve with their cores, and how the heaviest black holes form at all. We began with a paradox, a black hole eating faster than physics supposedly allowed. We end with a richer physics, one that includes magnetic fields, trapped radiation, and self-regulating winds. The cosmic guardrail wasn't wrong, it was just incomplete. Of all the explanations we explored, which one do you think is the most likely reason these black holes can eat so fast, and what would you name a black hole that breaks all the rules? Share your answer in the comments. Subscribe to continue investigating the universe's most stubborn enigmas and discover the surprising physics that powers the cosmos.